And although these things mean a little bit different, and but sometimes they are used interchangeably. So yeah, let's talk briefly about each one of them and see what's the difference. And generally speaking, the data science as a whole is, pardon? Is anyone saying something? Nope.
No,
Yes,
you can continue.
let me check. Okay, yeah. So yes, as you would have already heard or read it everywhere, like data science is interdisciplinary and it's an overlap between CS, stats, and business knowledge and stuff like that. But the way I would see is like regardless of no matter what subject or domain you use underneath it, uh, the main goal for data science is you want to deliver the business some value out of data they have. Now, you might need a little bit of software engineering and skills to do so. That's why there is CS on the list. You may need statistics to derive some inferences on top of the data that you have gathered. And the main important thing is business knowledge. And that's the reason that is very much important, even more important than the other things like the core CS skills, is because at the end of the day, you have to deliver value or impact to a business. And business folks are mostly non-technical, and you would have to learn, deal with them, understand their challenges and day-to-day in their day-to-day life and workflow, communicate with them, translate that business situation or scenario into a technical problem statement, and then you actually start working on your algorithm. And once you are done with everything, all of that, you also again need to communicate back to those business folks about what you did, because like no one actually considers or understands, like no matter how much accuracy or metrics you list down, but you need to translate the outcome or the impact of your models back to business terms. So yeah, that's why it's an overlap of all that. Now, along the in doing so, you may use other items such as machine learning. Well, what is machine learning? And yeah, there are like we can talk about technical aspect of it and name algorithms and stuff like that, but I would be covering mostly at a broader spectrum. So when we talk about machine learning, it's just that contrasting it with traditional software engineering, wherein we are building some process or a function to get some sort of outcome. Instead of doing that, what machine learning tries to achieve is to use the data, which is like along with different features of it, and we already have the outcome in hand. We are trying to predict or estimate the function which closely resembles or can generate the output. So it's like when you compare it with that software engineering, it's like software engineering, the process or the function itself, which you are building to get or achieve some output, whereas machine learning is something different, where is it is we are trying to predict the function, and we already have the output or desired output out there. As you must be knowing, there are these categories of machine learning: supervised, unsupervised, and reinforcement learning. Well, there are certain things that needs to be considered within, while applying these algorithms, that we want our data set such that the training as well as tests are from the same distribution, and so that it is generalizable. Because when we are predicting function, it's not the training set itself on which we'll be running it. We want to generalize it onto unknown data sets. So that thing needs to be considered. Okay, quickly difference between what all of these three. Supervised is the situation or scenario where we already know the labels. Classification, regression are the examples. Classification wherein the output label is of categorical type. Regression is where the output of target is of numeric type. And unsupervised is where we don't know the labels, but we are trying to group some things like cluster something or things like that. And reinforcement learning is something like feedback reward system. So all of these automated programs which are playing games like chess and AlphaGo and stuff like that. So what's happening over there is essentially the model itself will be, it doesn't have an absolute path, but it can infer whether it's going in the right direction, whether any step taken is correct or wrong, based on the reward or penalty it gets. I would take a moment over here and give you an analogy which you may be able to use somewhere while talking to business folks or non-technical people, like talking about supervised learning. It's something, okay, let's say I don't know a route or a path to, let's say from GLS University to Riverfront, right? I'm new to the city and I need someone's help, guidance about how to reach there. Someone can take me there once, twice, and a couple of times. Eventually, I'll familiarize myself and I'll be able to reach there on my own. So what we are doing in machine learning is nothing but the same thing. We are exposing our model with multiple observations, like instances of data points, and it learns underlying features, and it tries to predict things on its own after getting trained sufficiently. So that's what it is. Again, there is a concept of
Hello.
overfitting. Yep.
Hello.
Yes.
Hello, Mr. Vishal.
Yes, I am. Yep. Do you have any questions?
I think you are not audible.
Okay. Can you hear me now?
Hello.
Okay. Should I change the audio connection and reconnect?
Now you are audible.
Okay. Got it. So, yes, going back to what I was speaking, it's something like we are exposing our model with a number of instances or observations, and it will learn its underlying features and tries to predict on its own. And now there is a concept of overfitting and underfitting that needs to be considered while you are developing such kind of models, because again, giving an analogy, like when someone is showing me the path that I don't know, I can pick up on essential features as compared to non-essential one. That's the thing that we want. But sometimes when we try to overtrain or like give assigned parameters which tries to achieve 100% accuracy and so on, essentially what we are doing is we are overfitting, and we are just trying to replicate what we saw during training phase. So, well, in this scenario, it would be something like, okay, let's say that there was a cow sitting at a junction, and we need to take a left from that. Now, cow is a dynamic component. We do not have to think it as one of the landmarks that while remembering a path to some place. Whereas, let's say that there is a statue, something permanent, more permanent, we can think of it as one of the features while remembering the path. So if you try to pick up on some things which are not necessary or suppose you shouldn't be picking up, in that case, it is called overfitting. If you are not even picking up essential components or features, and in that case, it is called underfitting. It's like, okay, go straight from here. Well, how straight? So these are the different things or issues while training. And in terms of analogy with unsupervised learning, it's something like, okay, you want to group everything together, which has something similar, something in common. Let's say that animal which are having 4 legs, 2 ears, and everything can be categorized into, like broadly speaking, animal. But if you add a more feature, let's say that it also has 2 horns, in that case, it might be a cow and not a dog or a cat. So that's something like we do not exactly know what we want. There's no label by training, but based on certain characteristics or features, you are trying to group things, and these can be fall under unsupervised learning. So yeah. And reinforcement learning, giving an example, it would be something like, okay, when you deal with small kids, it would be something like, okay, if a child does something good, you reward them, right, by handing out chocolates or something like that. And if something that the child does is wrong, then you at least show them and teach them, right? So that's what something similar is with reinforcement learning. Now, since we talked about machine learning, I would also bring in some other terms because those are highly similar. When you open up any textbooks of machine learning or data mining or stats, you may see that all of them contains more or less the same topics. All the algorithms are same. Then why are they different subjects? Well, most of the time it's less that it's a different take or a perspective by different academic school of thoughts. That's it. And data mining is something where we are trying to look at data and discover something which is not apparently visible. It might be different kind of patterns or inherent rules, some trends or something like that, associations. So we are trying to uncover that with a broader goal of knowledge discovery. So that's what data mining aims to. And data mining, yes, you can think of it as more or less same things, including databases. Now, statistics. Statistics, the algorithms are same. Again, everything is same. It's just from a mathematical perspective. When you read a textbook, it will be more about the terms are used are a bit different, but referring to the same things. And overall, the goal of stats is like we are trying to estimate things based on approximations and stuff like that. And since we are dealing with approximations and estimations, leveraging probabilities and distribution and all that, and those concepts are like frequently used, highly exploited over there. Natural language processing. Okay. So again, broadly speaking, this is a part of artificial intelligence. the aim is to deal with language the way we humans do. Um, Machine learning can be used for some approaches for natural language processing, but it's not just that. We can also leverage rule-based approaches, the concepts which are part of theory of computation and compiler design, automata and stuff like that. You must be remembering it from undergrad and stuff like that. Yeah. So yes, there is an intersection of natural language processing and machine learning, but those are two separate things. While computational linguistics is actually same as natural language processing, but that term is frequently used by folks from linguistics background, because the perspective is like, okay, we want to make use of computers to learn, understand, and generate a language. So that's what computational linguistics is, whereas natural language processing is the same thing from the perspective of computer science, AI. Okay, I think there's another slide. Okay. Popular NLP tasks out there, you must have heard of it. I won't go much into detail. But yes, some things like machine translation and like word segmentation, even sentiment analysis, and all of these things definitely leverage machine learning.
Just a second, sir. Sorry to interrupt you. The students may not be aware of the majority of the terms that you are discussing. That is segmentation, tagging. So if you can brief them into the basic of what exactly these terms are, that would be great.
Okay, yeah, sure. I thought I'm digressing too much from data science. That's why I was trying to skip it. But yeah, let me give some background of each one of them.
Because they have not studied a subject called AI. They may be knowing these terms. May have heard of it, but exactly what AI is, what NLP, data mining, only few of them might be knowing. So I request you to give them an introduction to what exactly these terms are.
Yes. Okay, sounds great.
Yeah. Thank you.
Yes. So the way, okay, going back to when I said that we can use machine learning for some approaches and also other things, what I meant was, let's take an example from the actual practical tasks. Interactive systems are nothing but maybe dialogue systems or chatbots or something where you would be interacting with the program and it would be able to respond to your inputs. Again, there are different ways to approach any problem. Let's say that there used to be something called ELISA, that was a program or early versions. Okay, rather than not going into the specifics, but early versions of chatbots used to be prepared answers. Okay, if you see these kind of keywords within a question, then you respond with these kind of answers. That's one way to do it, a naive way to do it. And there is no logical consistency between multiple questions that you, or multiple interactions happening between the chatbot and you. Let's say that we can say something like, okay, how about that? You can refer or point something back in time, and the system won't be able to reply to that. That's one of the item. But yes, we have come across a long way by training algorithms, and now we have co-reference resolution and stuff like that to address those kind of problems. So other things, the way machine learning can be used is, since machine learning is not hard-coded, this is one of the major differences between software engineering and machine learning, wherein software engineering is like the path is absolute. The thing that you want to achieve, you already know what you would like to do. And the steps are very much clear. Okay, let's say that you are developing a website and you are a web developer. You want to build a form. You know that this has to be a text box. This needs to be of this type, input type. And once you submit, it should go to database and so on, blah, blah, blah. But in machine learning, there is no absolute approach that, okay, this is how you solve it. It's just that your data would be changing dynamically over time. The quality of the data, the features might change, and that's why you need a mechanism, a machine learning model, which will be training on its own over the period of time. It takes in the feedback that user provides as its input and reiterate and improvise itself over time. So that's something better or good thing about machine learning. Okay, just going back to the list, natural language understanding, natural language generation. This is something like the program itself should be able to understand language. Understanding language is very complex because language is ambiguous. Depending on the context, a single word can mean something different. So that natural language generation, wherein once you understand, the program understands something, it should also be able to generate language, text, or even speech, which feels like human-like. Like there is a Turing test, right? Something like that. So basically, we are not there yet, but we obviously would like to improvise the current state of the art. So these are the open natural language processing tasks, and whatever that fancies your interest, you might want to dive deeper, because these all are literally semester-long subjects if you choose to specialize in those. But yeah, summarization, it's like paraphrasing and a huge block of text into a small summary. And meaningful summary covering all the important points. That's again a challenging task. Information extraction. Let's say that there is a lot of manual effort involved in pick out or extract some of the information, which humans can do pretty easily. Let's say that I used to work as natural language processing engineer, and there were bioinformaticians which used to look at the patents, where all the drug names are specified, all the combination, and how much the quantity of the drug and what kind of mutations used to happen and stuff like that. So basically what happens is we can understand all those things easily, we can extract, but it's a manual effort. You would like to automate that kind of stuff, right? So doing that using rule-based approach or machine learning-based approach falls under information extraction. Machine translation, and that's nothing new. You already are using Google Translate and other stuff like that. So there, again, it definitely needs improvement, because not Google given translated statement is as good or equivalent as what a human bilingual person can translate. So that word segmentation, well, it's pretty straightforward and easy in terms of languages like English, but for languages like Chinese, where there is no white space between two different words, the entire sentence is just a single string, or it can happen over like that. So you need different mechanisms to break down and tokenize and like figure out where is the boundary of that word. So that's word segmentation. Sentiment analysis broadly, how is the overall sentiment, whether the text covers positive sentiment, negative, and neutral, and you can categorize and create more number of bins, strongly positive, strongly negative, slightly, moderately, whatever. That's up to us while training the algorithms. But yeah, you got the gist. Tagging, again, the standard task is part of speech tagging that comes at a very basic level, but you can leverage machine learning to tag literally anything. It's like instead of part of speech, you can train the machine learning model to say that, okay, whenever this kind of occurrence happens, then label that word with something. So that's tagging, chunking, again, that breaking down syntax and parsing, okay, and text categorization. We can create, as per the business needs, create our own categories and place the text after analyzing. Artificial intelligence. Now, the reason that I have included this slide is since we talked too much about this machine learning, natural language processing, and stuff like that. So now, artificial intelligence is a big and broad, the mega subject, and machine learning, natural language processing, all those are subsets of AI. You may be hearing about hearing people saying that, okay, we are AI-driven, AI is doing everything, and so on. Well, actually, AI is nothing but we are trying to replicate intelligence found in like natural life, right? Out there in animals, in humans, and so on. So the way we try to replicate is like we figure out what are the characteristics or the items which define intelligence. So the way we keep organize our knowledge, how do we learn, how do we make reasoning, how do we understand language, communicate with others, how do we perceive things, all of those things fall under the umbrella of artificial intelligence. So relating it with other topics which you may have heard in other items are like, let's say that ontologies, if you have heard of it, the way you store data and like interlink with each other by pointing out, okay, with different kind of relationships of items. That can be considered as a part of knowledge representation. Machine learning and all those stuff can be part of this learning. Natural language processing can be part of this thing. And even the subjects like computer vision and so on, which helps machine perceive the life around them, are part of AI. So yeah, just broadly speaking. Okay, now we covered a lot about different things. Now, the reason that we should also be aware of big data is that, again, I haven't named any of the algorithms yet, and I'm not going to dive into those things. But let's say that you have all these algorithms, right? You are learning scikit-learn library, you have naive Bayes and SVM and stuff like that. And you train your model, you predict something. Everything works fine when the data is small and reasonable. And most of our demos at the universities would be smaller in size, right? But as soon as the data starts getting bigger, it starts growing, it will become more and more of difficult to train a model which is generalizable enough. And firstly, it may also be the case that the computer, like you will be running out of memory pretty soon. You will face out of memory errors. So when you can say that you need to know of big data, either of these cases can indicate that you are in the need of big data skill set. One is either it is too big, the data is too big to be stored on a computer and processed. Second thing, let's say that data is not big enough, but the overall computation that needs to be done is taking too much of time, and it's pretty much unreasonable to be finished within a single reasonable amount of time on a single machine. So that can be an indication that you need big data. I can give you an example for both. One is, let's say that you have uh, so much of streaming data. Let's say that you are hosting some sort of Ola or Uber or something like that, right? That kind of application, and there's tons of user base, and there are requests coming in and out every second, lots and lots of them. In that case, you definitely need some way to deal with it and deal with a streaming data source as well as process it and store it and stuff like that. And it cannot be quite efficiently done on a single machine. So that's where there's many number of instances or data points. The other thing is like a mathematical, let's say like problems which are core to these items, like astrophysics and stuff like that, where there are computations that needs to be made. Computations such as like the huge derivatives. Like even if it's not computation, let's give you a simple example. Okay, like we are trying to crack a password. We do not know a password. It's a combination of this thing. Giving you a simple analogy, it's like a single person trying out different passwords, like set of items. It will take a lot more time, right? But if you divide it among multiple people, that okay, you try this range, you try this range, it will be much more faster. So it's not that data is huge, but the computation can be distributed across multiple systems. So yes, the main benefit are things that we desire out of big data are like scalability and high availability. Once you set up a cluster or something infrastructure, you can add on more and more nodes to cluster with a very little amount of effort in terms of configuration. And the availability of data would be higher if you increase your application factor by some amount, reasonable amount. So like if one system goes down, the data can be retrieved from other replica of it within the same cluster. So what we are leveraging is distributed and parallel processing in this case. So yeah, you may need to do that. And finally, data visualization. People may not talk much about data visualization while talking of data science, but this is very much an important step because at the end of the day, non-technical business folks would be more open and perceptive about visualization, charts, graphs, plots, and stuff like that, as compared to the statistics that you might be pulling out. Okay, that those stuff. Okay, yeah. So definitely, data visualization is a nice way to deliver, communicate the gist of it with less technical details. Okay, now we talked a lot about different things, how we may need different skills while dealing with a data science project. Now, let me talk a little bit about the overall life cycle of a project. And let's say that you are a data scientist and you are approached by some firm or company, some manager, and you want to build something out of it, right? Then what are the steps, the sequence of steps that you might be taking? So this is what is how the steps will proceed. first of all, again, this is not a hardcore or bookish rule book that you need to follow these steps. It all depends on the setting, the team that you're working at. Some teams are big and resourceful enough to have each of these tasks dedicated to a separate resource. Some teams are very small and where each of the tasks needs to be done by a single resource. So it all depends on the setting. But it's always nice to know if you know like more and more stuff about the entire thing, and that makes you a valuable asset to the team. So yeah, let's say that these are the steps. In case you are the only person or data person or lead data scientist on the team, in that case, you would be first talking to subject matter experts or the stakeholders or the folks that are desiring to get some benefits out of it. Yes. Any questions? Okay. Let me continue. So you would like to talk to business people about, okay, what are their expectations, what kind of workflow they have on their day-to-day life, what are the business problems that they have and things that can happen, and how. That's where you will be figuring out where you can deliver value with your technical expertise. And for that, there would be some, I can say that, okay, some sort of interviews wherein you talk about what are the data points and how you can make the life easier for business with your models and stuff like that. So, and once you have decided that, the second thing would be sourcing of the data points that are required for your model, to train your model. Now, sourcing this particular step may need different kind of skill sets depending on the kind of data sources that you have. But basically, this is where you would be needing more and more software engineering skills, like knowledge of databases. If your database is of different variety and all this big data, then you might even need NoSQL database knowledge, and as well as big data and stuff like that. But yes, if you do not need it, don't try to put it in everything. Like, it's okay. Cleaning. This is essential part before starting out modeling, because in real life, when you look at the data points, it's not always clean. When I say clean, there might be certain things that you need to consider before proceeding to this modeling phase, which is like, let's say that there are certain values missing while filling out the form. There are certain fields which are not mandatory, and people just skip to fill it, or even if they are mandatory, they would be just putting things like not applicable or something like that, right? In that case, that's not actually adding value to our analysis. Again, it depends. In certain problem statements, it may. In some certain use cases, it may not. So that's where you decide what to do with those kind of situations, whether you want to remove it, those kind of records with missing values, you want to replace it with average values or something like that, and that. So that if you are dealing with text data sources, then you might want to remove stop words and like lowercase and the standard text processing steps, and figure out what all things will make sense in your analysis. Then comes exploratory data analysis. This is the step where you would be like start exploring how the nature of the data is. You can start it with basic descriptive statistics, which like figuring out mean, median, mode of numeric columns in case of categorical columns. How many records are there? Like you can create different charts and so on to see and figure out the basic stuff. The second thing that we can do in EDA is like maybe if there are multiple features which are highly correlated, it will actually have an adverse impact on your model, right? So in that case, you would want to identify those in this step. So giving you an example, like the standard textbook examples which you might have heard of are these like housing price prediction and so on, regression models and so, right? So there might be features columns in your training data like number of rooms in the house, the square footage of the property, and so on. Well, those are actually directly proportional, right? The more number of rooms, definitely the more number of square footage there would be. So there has to be some sort of correlation in between those features. Now, up to some extent, it's fine, but if in real life, like certain columns which start having more than a threshold correlation, it's not good for your model and the training. So there are certain statistical methods that you can leverage to figure out the correlation coefficient between the features and remove which are below higher than certain threshold. You may want to do certain pre-processing and feature engineering. And again, not always all the columns that you get in a training data are useful. Sometimes you may want to build these on top of the existing one. You may manually hand engineer some of the features. Sometimes you may want to discard the ones. So that things happen over here. Features, if we create our own or build something on top of which are existing ones, that's feature engineering. And if we select something and deselect or like discard the rest of them, that's feature selection. Modeling. This is where all that standard stuff happens, all the algorithms, application of it, and then evaluation of that model. But that's not the way things end. The reason that we are emphasizing on the entire life cycle is because mostly when when you take all this data science class at school and even on online classes or something like that, mostly they'll be talking about all the models and stuff like that, right? But that's something which typically data scientists spend least amount of time. The rest of the items is where you need to put more effort and time to make a successful data science product or like project. The data product part is you need to think, okay, once you have built your model and everything, who is your target audience and how they would be able to consume whatever you did in terms of modeling. And if the other team is technical enough and they will be integrating your machine learning solution to their web application or something else, then you can even serve it as an API. If it's a totally non-technical person and only interested in seeing graphs, charts, or reports, you can create that out of it. Or like, let me give you an example. I created this anomaly detection model for our department. So the department's mandate was to look for compliance across different verticals within the organization, and then act upon instances or occurrences where there is something concerning. So anomaly detection algorithms can be used to figure out where things are odd or something that is unusual from the normal thing. Giving an example like the notification, SMS notification or email notifications that you might receive while banking with some bank, right? If there is an unusual or suspicious activity in account, it will be notified using an email. So that actual algorithm is a machine learning model, but the way it is delivered or built into a product is that a software like a program which will use this algorithm, and then based on whatever the outcome is, you would be receiving an email or something like that. So that's also something where software engineering skill sets will be required. And at the end of the day, no matter how much good things that you do, you also need to communicate back to business. So that's the last step and first step. And this is where soft skills come into picture or importance. So again, business folks might not be interested in looking at 90% accuracy of your model, but you again need to show that this is what the model means, and this accuracy of this outcome or results means that your business would be saving this much of money or cost cutting or something like that. Basically, you need to translate your technical outcome or results into business value back to leadership or management. And since we highlighted a couple of times the software engineering skill sets, it is these days in the realm of data science referred as data engineering. It's like software engineering that is required to do in this life cycle of data science is basically called as data engineering. And that needs knowledge of databases, productionizing stuff, and MLOps. What this is like at the time of modeling, let's say that your team might be having so many different data scientists working on the same thing, right? And you need to figure out a better way to collaborate, maintain which model is in production, and all the parameters that we have set for that. So those are the things that we need to consider in terms of software engineering with respect to data science. Okay, now tools, technologies, and frameworks and the languages. Again, this is very subjective. It doesn't matter. No matter what you use, you can always code it in any language. But the reason that people prefer some languages over other is because there are off-the-shelf libraries available on for some of the programming languages. That's the reason. Python has been a popular choice. After that, R, because statisticians typically tend to prefer R because it's not too much of like a programming language. It is something similar to MATLAB. And Scala mostly preferred for big data things, all the Spark and that processing part. You can also do it in Java. Most of the big data frameworks are JVM-based tools and frameworks. That's why these two languages, but most of the modeling, people prefer to use Python. Again, don't get me wrong, you can develop a machine learning model in any other language, but it also depends on the community support of that programming language itself. Python happens to be a language of choice because there are libraries such as these. So, like, point Pandas, that's a library where it provides a nice interface to deal with tabular structure, tables, and stuff like that. NumPy for arrays, multidimensional arrays also. Scikit-learn for all the pre-implemented version of machine learning algorithms for classification, regression, and so on. Keras, PyTorch for neural nets and deep learning. NLTK, GenSim, Spacey for natural language processing. Stats models for statistics. It has pre-implemented versions of time series analysis and so on. So that typically a data scientist would be using Jupyter notebooks and to interactively develop and SQL for basic level of SQL knowledge. And to develop visualizations, you can either use off-the-shelf vendor-based products like Tableau and Power BI. If you are a web development background and are comfortable with JavaScript, I highly recommend looking at d3.js. It has quite good-looking production-grade visualizations. And if you want to develop within Python itself, these are the libraries which typically are used to generate visualization. Now, tools and technologies within big data definitely need a more different slide because it's a whole new world out there for that. It's something, so many different tools depending on your need and requirement. Again, it's not necessarily used everywhere. It depends on the use case and your business need. But just to quickly summarize, what are the tools used in which step of the pipeline? If you are dealing with streaming data, you may use Kafka and so on. So ingestion, that happens at the sourcing step of the data science lifecycle. You might want to use certain tools. Then you also need to consider a format which are efficient in storage as well as the serialization. We definitely need a different file system depending on if you are using a big data ecosystem, then SDFS. If you want to use cloud and so on, you need to consider other things. If your model works on batch processing, ETL pipelines and so on, then these are the tools that you might want to use. If you are dealing with stream processing on the fly, then there are other tools out there. Most of the tools are written in Java or Scala or something like that. So it's like that's where the later part of that JVM-based languages comes into picture. Machine learning-based algorithm, as I said, that you can develop a machine learning algorithm on top of this basic smaller data sets using scikit-learn and so on. But if you are developing a machine learning model on top of big data, then you might want to look at Spark, MLib, and so on. If you want to perform SQL on big data sets, then these are the tools. Now, depending on the need, you might also look at different kind of databases. Relational are the traditional ones that we typically use, but sometimes there are occasions like we do not necessarily have a predefined schema, and the data set is coming out of some sort of API, and the number of fields which are returned by the API may not necessarily be the same every time, and we do not know how many fields are there. So if let's say that we do not have a data dictionary and so on, we might want to use MongoDB or so, something like that. Elasticsearch and so on, that's for text search and so when you want to dump text into it and later on search or make queries on top of text. If you are more interested in traversing relationships and plotting it into a graph, then yeah, Neo4j. Yeah. And again, most of the things in big data will require some level of management since it is distributed across multiple machines, and that's where you also need to be aware of cluster management tools, which are these. Okay, I won't dive deeper into each one of them, but yeah, that was just a summary. Now, in terms of recommended items, I would say these things um, for statistics. ISLR is a book, Introduction to Statistical Learning with R, and then Elements of Statistical Learning. These links are out there. I'll share the slides with the host. And these URLs do have the entire PDFs available out there. So that I also highly recommend Data Science Specialization, this thing on Coursera, and that's because it emphasizes on the entire life cycle of data science, how you would approach a problem very nicely. That's why I would recommend that. If you want to understand machine learning algorithms, each one in detail, and these courses have it very well explained. This Andrew NG is like the standard source of for machine learning content. If you are interested in natural language processing, then Jurafsky and Martin, again, that's, I believe there is a web course also out there, and there's a book there as well. So URLs are there. So, okay, so these are the career paths, although each one of them are different. The focus might be different, roles and specific roles and responsibilities might be different, but these are the generally titles available out there once you have all these skill sets. And take these titles with just a grain of salt. You may or may not need other skills at your role as well. And lastly, I would like to talk about expectations versus reality about data science, because yes, this is something trending and highly popular, and everyone wants to do it. But there are some things that needs to be considered while performing your duties as data scientist. I would say you do not necessarily need overly engineered solutions always. Like sometimes, if you are able to get things done with very simple and straightforward approach, do that first. Just because of the fact that you learned, let's say, that NoSQL at your university, you need to make use of it in your project. That's not the case. And well, if you have the luxury and liberty to experiment, then that's fine. But some of the things, the restrictions also might come into picture because of business restraints on budget and so on, because everything you would have to justify it. It's not like just because we want to do it and so on. So yeah, start simple. Like just giving you an example, like in terms of machine learning algorithms, people will be very much keen and hyped up about all this deep learning and neural nets and so on, ensemble models. But you need to make a case for making use of those advanced algorithms and justify why do you use so-and-so algorithms. If you are able to get things done within reasonable, like generate reasonable results with a plain and simple algorithm, then that's also fine. That's great, actually. Second thing is, it's like you would actually have to deal with non-technical people more than you think in the domain of data science. So it's not like just knowing all the algorithms and so on that is all that you need to become a data scientist. It's more than just modeling. Soft skills and software engineering is far more important than knowing the algorithms itself. In fact, everything else, like you can read documentation and catch up on technical aspect, but I would say soft skills are the most important one. And yes, while learning online or at university or anything, we typically are shown with plain, simple, straightforward demos. That's not necessarily the case in real life. And there is a lot more effort that goes into defining a problem statement and translating into a technical problem. And it's not always as simple or as straightforward as in those small demos. So the cleaning of data and again, whether it would be of any use moving ahead or not. So those are the things that you definitely need to look at. And lastly, I don't think I have this. Okay, there was an image just for laughs. That's it. And thank you. I guess that's about it that I want to have. Thank you, everyone at GLS University for providing me a platform to speak and talk about my experience. If anyone has any question or anything in particular to talk about, I'm happy to accommodate that.
Thank you so much, Mr. Vishal Shukla, for delivering such an informative session. Students, are you having any queries? Would you like to ask it out?
I guess silence is no.
Just a second. Students, yes? Anyone is having any queries regarding whatever the sir has discussed right now? All right. What about the others? All right. I guess they are clear with the things that you briefed them. Thank you so much. Thank you so much, sir, for delivering such a wonderful session. I hope they are keenly interested in data science and they opt for data science as a career. Definitely, you briefed them about the various job perspectives. I hope they will think about it and I thank you on behalf of Faculty of Computer Applications and IT. Thank you so much, sir.
Yep, thank you. And if anyone has any questions in future, like anyone needs some sort of guidance or like just want to talk about anything, feel free to reach me out on LinkedIn or anywhere. It would be fine. Yeah.
Sir, can you drop your email ID and email ID in the chat box?
Yes. Where is it? Okay. Let me everyone and. Okay, I have put in my email address over there. You may use that. Yeah, that's fine. Okay. I think I am stopping.